In particle physics, the strong interaction is the mechanism responsible for the strong nuclear force, one of the four known fundamental interactions of nature, the others being electromagnetism, the weak interaction, and gravitation. Despite only operating at a distance of a femtometer, it is the strongest force, being approximately 100 times stronger than electromagnetism, 1,000,000 times stronger than weak interaction, and 1038 times stronger than gravitation at that range. It ensures the stability of ordinary matter, confining quarks into hadron particles, such as the proton and neutron, the largest components of the mass of ordinary matter. Furthermore, most of the mass energy of a common proton or neutron is in the form of the strong force field energy. The individual quarks provide only about 1% of the mass energy of a proton. The strong interaction is observable in two areas. On a larger scale, it is the force that binds protons and neutrons together to form the nucleus of an atom. On the smaller scale, it is the force that holds quarks together to form protons, neutrons, and other hadron particles. In the latter context, it is often known as the color force. The strong force inherently has such a high strength that hadrons bound by the strong force can produce new massive particles. Thus, if hadrons are struck by high-energy particles, they give rise to new hadrons instead of emitting freely moving radiation. This property of the strong force is called color confinement, and it prevents the free emission of the strong force. Instead, in practice, jets of massive particles are observed. In the context of binding protons and neutrons together to form atomic nuclei, the strong interaction is called the nuclear force. In this case, it is the residuum of the strong interaction between the quarks that make up the protons and neutrons. As such, the residual strong interaction obeys a quite different distance-dependent behavior between nucleons, from when it is acting to bind quarks within nucleons. The binding energy that is partly released on the breakup of a nucleus is related to the residual strong force and is harnessed in nuclear power and fission-type nuclear weapons. The strong interaction is hypothesized to be mediated by massless particles called gluons, that are exchanged between quarks, antiquarks, and other gluons. Gluons, in turn, are thought to interact with quarks, and gluons all carry a type of charge called color charge. Color charge is analogous to electromagnetic charge, but it comes in three types rather than one that results in a different type of force, with different rules of behavior. These rules are detailed in the theory of quantum chromodynamics, which is the theory of quark-gluon interactions. After the Big Bang, during the electroweak epoch, the electroweak force separated from the strong force. Although it is expected that a grand unified theory exists to describe this, no such theory has been successfully formulated, and the unification remains an unsolved problem in physics history. Before the 1970s, physicists were uncertain about the binding mechanism of the atomic nucleus. It was known that the nucleus was composed of protons and neutrons, and that protons possessed positive electric charge, while neutrons were electrically neutral. However, these facts seem to contradict one another. By physical understanding at that time, positive charges would repel one another and the nucleus should therefore fly apart. However, this was never observed. New physics was needed to explain this phenomenon. A stronger attractive force was postulated to explain how the atomic nucleus was bound together despite the protons' mutual electromagnetic repulsion. This hypothesized force was called the strong force, which was believed to be a fundamental force that acted on the protons and neutrons that make up the nucleus. It was later discovered that protons and neutrons were not fundamental particles, but were made up of constituent particles called quarks. The strong attraction between nucleons was the side effect of a more fundamental force that bound the quarks together in the protons and neutrons. The theory of quantum chromodynamics explains that quarks carry what is called a color charge, although it has no relation to visible color. Quarks with unlike color charge attract one another as a result of the strong interaction, which is mediated by particles called gluons. Details. The word strong is used since the strong interaction is the strongest of the four fundamental forces. Its strength is around 102 times that of the electromagnetic force, some 106 times as great as that of the weak force, and about 1038 times that of gravitation, at a distance of a femtometer or less. Behavior of the strong force. The contemporary understanding of strong force is described by quantum chromodynamics, a part of the Standard Model of particle physics. Mathematically, QCD is a non-abelian gauge theory based on a local symmetry group, called SU. Quarks and gluons are the only fundamental particles that carry non-vanishing color charge, and hence participate in strong interactions. The strong force itself acts directly only on elementary quark and gluon particles. All quarks and gluons in QCD interact with each other through the strong force. The strength of interaction is parametrized by the strong coupling constant. This strength is modified by the gauge color charge of the particle, a group theoretical property. The strong force acts between quarks. Unlike all other forces, the strong force does not diminish in strength with increasing distance. After a limiting distance has been reached, it remains at a strength of about 10,000 newtons, no matter how much farther the distance between the quarks. In QCD, this phenomenon is called color confinement. It implies that only hadrons, not individual free quarks, can be observed. The explanation is that the amount of work done against a force of 10,000 newtons is enough to create particle-antiparticle pairs within a very short distance of an interaction. In simple terms, the very energy applied to pull two quarks apart will create a pair of new quarks that will pair up with the original ones. The failure of all experiments that have searched for free quarks is considered to be evidence for this phenomenon. The elementary quark and gluon particles affected are unobservable directly, but they instead emerge as jets of newly created hadrons. Whenever energy is deposited into a quark-quark bond, as when a quark in a proton is struck by a very fast quark during a particle accelerator experiment. However, quark-gluon plasmas have been observed. Every quark in the universe does not attract every other quark in the above distance-independent manner, since color confinement implies that the strong force acts without distance diminishment only between pairs of single quarks, and that in collections of bound quarks, the net color charge of the quarks cancels out, as seen from far away. Collections of quarks therefore appear without color charge, and the strong force is therefore nearly absent between these hadrons. However, the cancellation is not quite perfect. A small residual force remains known as the residual strong force. This residual force does diminish rapidly with distance, and is thus very short range. It manifests as a force between the colorless hadrons, and is therefore sometimes known as the strong nuclear force or simply nuclear force. Residual strong force. The residual effect of the strong force is called the nuclear force. The nuclear force acts between hadrons, such as mesons or the nucleons in atomic nuclei. This residual strong force, acting indirectly, transmits gluons that form part of the virtual pi and rho mesons, which, in turn, transmit the nuclear force between nucleons. The residual strong force is thus a minor residuum of the strong force that binds quarks together into protons and neutrons. This same force is much weaker between neutrons and protons, because it is mostly neutralized within them. In the same way that electromagnetic forces between neutral atoms are much weaker than the electromagnetic forces that hold the atoms internally together. This fact, together with the less rapid decrease of the disruptive electromagnetic force between protons with distance, causes the instability of larger atomic nuclei, such as all those with atomic numbers larger than 82.